Okay, so to do the hypothesis testing, we have many steps. Number one, we have to know what parameter we are testing for. What we are doing, we are testing for uh, mean, the population's mean or population's proportion. So we have to determine the population parameter of interest. This is important. The other step or the next step is going to be identifying the hypotheses of interest, then formulating the hypotheses. Before we take an example, so we have to show something. We have to say something here that the null hypothesis always contain the equality sign. So it's going to be either equal or less than or equal or greater than or equal. So the equal sign is always attached to the null hypothesis. The alternative hypothesis is going to be the opposite of what we have. If you have equal here, the other one is going to be not equal. If you have less than or equal, the other one is going to be greater than. If you have a greater than or equal, the other one is going to be less than. Okay, which is the alternative hypothesis. So based on the sample data that we are going to collect, we are going either to reject the H node or we do not reject, or we fail to reject H node. We do not accept H node because it's an assumption. And we cannot make our decision based on one sample, okay? We cannot accept the null hypothesis, but we reject it or we fail to reject it. We reject it and we fail to reject it. And let's go to an example. In today's economy, university students often work many hours to pay for high costs of a college education. Suppose a university in the Midwest is considering changing its classes schedule to accommodate students working long hours. The registrar has stated a change is needed because the mean number of hours worked by undergraduate students is more than 20 hours per week. So the registrar now is claiming something. He said something unusual. He says something that opposing the default situation. And first of all, if you look at the scenario or the question is talking about the mean, the average. So we are speaking about the population mean, not population proportion. This is important. The question says, let's formulate the null and alternative hypotheses. The null hypothesis is the scenario where the mu is the default situation, which is less than or equal 20 hours. Because the registrar said, oh, students, they work more than 20 hours per week. He's claiming this. We have to test now, but we have to formulate first the hypotheses, right? So the first one is the null hypothesis. That one involved the equal sign. If you read the context, you can figure out the null hypothesis by two ways. Number one, the statement doesn't say any equal sign here, so this is going to be your alternative hypothesis. He says the mean is exceeding 20 hours, so this is your alternative hypothesis. Or you can think about it in terms of in terms of the definition that we said. We said that the null hypothesis were the default situation. The registrar now says something else. Says, oh, we have to change the schedule because we have to make accommodation because students work more than 20. Okay, you don't have any evidence. So that's why this is the alternative hypothesis, okay? The greater than. Less than or equal is going to be the null hypothesis. This is one example. Another example, let me just put a line here, draw a line, and give another example. Suppose we are talking about the sodas cans. Okay, the sodas can, maybe. Not maybe. We know that the sodas can, the average amount of liquid is equal to, I don't know, is it 16 or 14? Maybe 14 ounces, I don't know. 14 or 12. And the alternative hypothesis, the soda is not containing 12. Maybe we have some kind of error. Someone claims that, hey, my soda doesn't contain 12, or we took samples that some people said it doesn't contain 12. It's actually different than 12, maybe more, maybe less. Or let's say the production manager or the operation manager, the production manager, basically he says that, okay, let's take a sample and see whether the cans contains. This is the advantage. Look at the hypothesis testing. Because in factories, they will not be able to collect all of the cans. They're going to take only sample of the cans. They're going to take like 50 cans to check whether these cans contains the 12 ounces or no. So the null hypothesis, which is the default situation, that the mean is equal to 12 ounces. Other than this, is the alternative hypothesis. The mean is not equal to 12 ounces. So the mean of the cans is not equal 12 ounces. That means if they found, look, if they ended up rejecting the null hypothesis, listen, if they ended up rejecting the null hypothesis, that means they are accepting the alternative hypothesis. That means the average liquid in the cans is not equal to 12 ounces. Oh, we have to do some calibration in our machines, right? So this is another type of null and alternative hypothesis. The third type is going to be something like this. As we said in the previous example, the average salary of doctors. We believe that the default situation, the doctors, the average, they gain above or equal 150, but someone claiming that no, the average of the salaries of doctors is less than $150,000. So these are the three scenarios that we are going to face when we formulating the null and alternative hypothesis, okay? Okay, again, you have to note something now. We are formulating hypotheses regarding what? The population parameter. This is the mean of the population. We are telling information about population, not sample. So then what? Then, because we are testing this, we are going to pick a sample. We are going to take a sample. Suppose we are picking n equals 100 in each of them. Because we have a sample, now, if you remember, we can do this. This is the sampling distribution. Why this is the sample? What do we get from the sampling distribution? As we said, the sampling distribution is helpful in a way that we know for certain that this is a mu, this is the population mean, this is the population mean, this is the population mean. Someone's going to tell me if the sample is not too large, we're going to use the t-test again, the same thing, as we did in chapter 8. We picked a sample. Then the sample is, suppose, okay, this is m equals 20, right? This is the hypothesized, listen, this is the hypothesized mu. This is a 12, and this is 150K, right? Dollar. Okay. Suppose we picked a sample, and we found that x bar is equal, suppose it's, let's say, is 21 hours. And here we picked a sample, x bar, and we got it contains 11 ounces, let's say. Wow. So they're cheating. And here we picked a sample and we found that the doctor, we found that some doctors, they kind of make the average 140 from the sample that we picked. Listen, again. Then, if I ask you to place these numbers down in the x-axis, you are going to tell me that the 21 is here, somewhere here. So this is my x bar, is 21. And this is 11 here. X bar equals 11. And this is 140 almost, somewhere here. X bar equals 140,000. Then you can simply say that, oh, from this sample, we found that x bar is 21, right? Which is greater than the hypothesized mean. That means, yeah, we are rejecting the null hypothesis, and we're supporting the registrar, claim that yes, students work more than 20 hours a week. This is not good. This is not enough. Listen, this is an important idea. Let's follow the same thing that I said there. So let's say here in the middle one that you found the average cans, the average liquid in the cans in your sample is 11 ounces. That means, oh, we have a problem in our machine. So let's figure out. This is again not enough. So let's again reject the null hypothesis. The mu is not equal to 12. It's less than 12 based on one sample, and we accept the alter. This is wrong. The same thing for the last scenario. We can't do this. We have to do something. We have to put the cutoff value. What does it mean? Listen, how far from the 20 we're going to accept the alternative hypothesis? If you take a sample and you got a sample of 21 or 22 or 20.5 or 23, So what is the average of the sample that you're gonna say at the end that, oh, we reject the null hypothesis and we accept the alternative hypothesis? How far are you gonna go to the right to accept that claim? How far are you gonna go to the left or to the right, because it's not equal? Maybe another sample you're gonna pick has like 13. So how far are you gonna go to the left or right to accept the alternative hypothesis? I'm saying accept alternative hypothesis means rejecting the null hypothesis, okay? The same thing with the last one. How far are you going to go to the left to be able to accept the alternative hypothesis and rejecting the null hypothesis? First of all, to do this, we have to differentiate between the three scenarios. Number one, the one in the left. We look at the alternative hypothesis every time we are going to look at the alternative hypothesis. The one on the left now, we have mu greater than 20. And the one on the right, we have mu less than 150,000. Both of these, the first one and the last one, we call them one-tail test. One-tail test, okay? Why it's one-tail test? Because we're going to focus in one region only. So in the example on the left, we are going to focus on the region of the right region. So the rejection, we're going to speak about the rejection region. The rejection region is just defined in one side of the sampling distribution. So which side is going to be is the side of the alternative hypothesis. For example, here we have mu greater than 20. Greater means to the right. To the right. So the rejection region is going to be to the right. And as I said, do you remember this? I said something. I said, okay, how far we are going to reject the null hypothesis? You have to give me the cutoff value, cutoff place. Maybe you're going to define this cutoff place here. You're going to tell me, okay, beyond this, if the sample that you got, listen, if the sample you got is greater than this value, we are going to reject the null hypothesis based on the sample that you got. Suppose that you specify this. You just told me that, look, listen, my cutoff value is going to be 23 hours. Okay, how did we decide this? We're going to speak about this. So this is the one-tail test. The same thing with the last one. With the last one, you may tell me, I'm going to specify the cutoff value. The cutoff value is going to be somewhere maybe here. If the average of the doctor's salary was less than this value, suppose that this is 145. If the average of doctor's salaries was less than 145 in the sample you got, we're going to reject the null hypothesis and accept the alternative hypothesis. The same thing with the first one. If the average of the samples that you took, of the sample that you took, if the average of number of hours from that sample is exceeding 23 hours, then we are going to reject the null hypothesis. Rejecting null hypothesis means accepting the alternative hypothesis. So so that's why we're going to call this one as a rejection region. Rejection region. Rejection region. Rejection region. Rejection what? Yeah, rejection H note. Rejection H note, okay? Rejection H note. This is the rejection region. And this is the cutoff value that you have to specify. What about the middle example? The middle example, it's kind of, we have two options. Why do we have two options? Because you said in the H note, mu is equal to 12. And we said the alternative hypothesis, mu is not equal. It's not equal to 12. It can occur on the left or on the right. The sample that you got could be other than equal. It's going to be not equal if it's greater than or it's less than. So that's why you have to give me cutoff values for both tails. Maybe here and here. You're going to tell me, okay, if it's exceeding that 13, we're going to reject the null hypothesis. If it's less than 11, we're going to reject the null hypothesis. We're going to reject that. What does this mean, basically? It means that, let's just put it that way. If you get an average, if you have a sample of cans and you got the average of the liquid in that, in this sample, and you got like 14 ounces. 14 ounces, what you are telling that 14 ounces is it's too far from the 12. That's why we're going to reject the null hypothesis and believe that we have something wrong with our machines. The same is applicable if the sample has an average of, let's say, 10 ounces in the left. Then again, you're going to tell me, oh, we've got a problem in our machines as well. It's too far from the 12. So these are the cutoff values. So these are the rejection regions. So that's why we call this one two-tail test, rejection region. Rejection what? Rejection H node, both of them. Rejection H node, both of them. So you're going to reject H node if your sample average is located in one of these regions. Okay? This is what we call the two-tail test. Two-tail test. So it can happen in either direction, right or left. Okay? And the full rejection region is divided into two equal parts, two tails, on the left and on the right. But the rejection region for the one-tail test is located in one area. Okay, that's cool. Now we have either one-tail, two-tail tests. But the question is, how to know how to know the cutoff value, how to decide the cutoff value. To decide the cutoff value, we're going to determine or to define something called significance level. What is the significance level? It's mostly going to be, in most of the examples, most of the scenarios, most of the industry, is going to be between 1%, 5%, maximum 10%. The significance level is connected to something called the type 1 and type 2 errors. Type 1 and type 2 errors. What is the type 1 and type 2 errors? The type 1 and type 2 errors. So let's talk about these two things. The type 1 error is rejecting the null hypothesis when it's in fact true. So you're going to commit type 1 error if you reject the null hypothesis, but actually it's in fact true. And the type 2 error is failing to reject the null hypothesis when it's in fact false. Failing to reject the null hypothesis when it is false. What does it mean by rejecting the null hypothesis when it's in fact true? So type 1 error, it occurs when the null hypothesis is true, but you made a mistake by rejecting the null hypothesis in favor of the alternative hypothesis. So it is the incorrect rejection of the true null hypothesis. The type 2 error occurs if you fail to reject the null hypothesis and you by mistake accept the null hypothesis, or it's the failure basically to detect a true effect or difference when it actually exists. So these are the table and we always assume the state of nature to be the null hypothesis to be true. So that's why we're going to focus only in this chapter about committing type 1 error. Type 1 error. So the state of nature, we're gonna assume always the null hypothesis to be true. If you conclude from your sample that the null hypothesis is true, or you do not reject the H node, then it's a correct decision. Don't reject, fail to reject. Fail to reject H node. If you fail to reject H node, then you have made a correct decision. If you rejected H node, then you're committing type 1 error. So type 1 error occurs when you are staying in this region. In this region, and this region, and this region. You're committing a type 1 error. Type 1 error. What does it mean? You are rejecting H node while H node is true, and this is the assumption. Again, this is our state of nature. Our state of nature is going to be null hypothesis is true. Our assumption is null hypothesis is true. We have no difference. Everything is the same, the default situation. If you reject this fact, then you are making type 1 error. Okay? Now back to the idea of the threshold. What is the threshold that we're looking for? This is what we call the significance level. It can be 1%, 5%, 10%. What does it mean by 1%, 5%, 10%? Actually, is the area. This is the significance level. This can be, let's focus on 5%. Let's just talk about the middle one, okay? All are the same. Let's say this is 5%. My significance level, we're going to call it alpha, okay, is 5%, which is the area on the tail or tails. 5%, this is going to be the 5%, the area. This is going to be the 5%, the area. What about the two tails? Yeah, they're going to be 2.5% here, 2.5% here. Okay, what does this represent? Listen, is the maximum acceptable probability of making a type 1 error. Is the the cutoff value, is the threshold value, is the maximum acceptable probability of making a type 1 error. For example, when a significance level is 5% is chosen, it means that you are willing to accept a 5% probability of incorrectly rejecting the null hypothesis when it's actually true. Okay? So the significance level basically sets the bar for how strong the evidence against the null hypothesis need to be in order to reject it. So now we know the maximum allowable probability for incorrectly rejecting the null hypothesis. This is our rejection region. So the maximum could be 5%. In very sensitive industry, they don't use the 5%. They need 1%. Like in medicine industry, they need to make it 1%. Because the default that the medicine is effective, no, they have to prove it's effective, the medicine. To prove it's effective, they don't want to have like a small amount of, they have to have like a very, they have to have a really small allowable probability to incorrect rejecting the null hypothesis when it's true. So they use the 1%, not the 5%. In business or in car industry or something, maybe they use the 5%. So back to our charts here. If you take a sample and this sample is exceeding the threshold, you can look at two things. Now, we have. Let me take one of them and go to have some space here. Okay. Let me take the one that we started with, the working hours. So the scenario says the working hours, the mu, the hypothesized mu. This is the 20. H naught is less than or less than or equal to 20, but we said the threshold we put here, this is the rejection region, this is the 5%. And suppose that we said it's 23 hours. Now what you have a sample. Listen, you have a sample. X bar is what? You got, let's say, 21 hours. Now, where is the 21 hours? The 21 hours is somewhere here. Let's say here. Maybe, number one, maybe you can compare X bar you got from the sample, you're going to call it X bar test, which is 21, with the threshold that you have specified, which is X bar, which is equal to 23, right? The one that you specified. We're going to call it X bar critical, by the way. You can compare these two and tell me the results. You can tell me, okay, my X bar test is less than X bar critical. The X bar test is the one that's taken from the sample. The X bar critical is the threshold, the cutoff value. Because it's a smaller than, it's not in the rejection region. So X bar test is not in the rejection region. So what does it mean, the conclusion? We fail to reject the null hypothesis. We fail to reject. Again, when we fail to reject this fact. So we come back to the registrar and tell him, hey, man, we don't have sufficient evidence. Look, we don't have sufficient evidence to support your claim. That the mean or the average, whatever, hours worked by undergrads is exceeding 20 hours a week So we got, oh, sorry, man, we don't have evidence to support your claim because we got, so we failed to reject H naught. We don't accept H naught. Listen, we don't accept because it's claiming, so we failed to reject it because it's just one sample, right? So we failed to reject based on our what? Cut-off value. So the first method is, listen, this is a very important. This is how we make the decisions. We compared, what did we do? We compared X bar test with X bar critical. The second method, or we can do something else. We can compare the area. Listen, we know that the rejection area is the rejection region is 5%, and you know 21 is here, right? You can simply look at this region. You calculate this region. There's no need to calculate it. It's clear, by the way, now. But when we do the math, we have to calculate. Is it greater than 5% or less than 5%? Yeah, it is greater than 5%. So you're going to compare the two areas, the area at the right-hand side of the 21 with the rejection region, which is this one, 5%. So the area, or we compare, in this example, the area on the right-hand side. In other example, if you have a left tail like this one, you're going to look at the area on the left, right? So we compare the area on the right of the X bar tests with the rejection region. Rejection region area, right? Rejection region area. And in this scenario, and always the rejection area, this is the significance level, this is the alpha. Suppose that, let's say this is, I don't know, 5%, this, let's say 7%. Okay? Again, this is not accurate chart. I make it just bigger for you to see. What do we call this one? The area on the right-hand side. Again, in this example, at the right. In the other sample, at the left. What about the here, or the overall area? The overall area. The region, the rejection regions. You add them, then you count. You compare it with the area on the right or in the left of the value that you got. So here, what do you call this area? It has a very important definition in the statistics. The area on the right of the X bar test, or on the left, it depends. We call it the p-value. So basically, if the p-value is greater than alpha, in this case we reject the null hypothesis. If the p-value is less than alpha, we fail to reject. In this case, p-value is greater, so we reject. Oh, sorry. P-value, here. P-value less than alpha, here greater than. Sorry for the confusion. If the p-value is greater than alpha, we fail to reject because we are not in the rejection region. If p-value is less than alpha, we reject the null hypothesis. Okay. In this example, the p-value in our example, the p-value equals 7%, which is greater than alpha, 5%. So we do what? We fail to reject. And this is the same as result we got from part A, or the first method, number 1. We failed to reject, so we don't have sufficient evidence to support your claim that the average hours worked by undergraduates exceeding 20 hours a week. Same conclusion. The third method, I'm just giving different methods. We have to know all of them. The third method, something related to chapter 6. It's very simple. Let me just put it here, okay? Do you remember what is this? Let me write them down. So this one, we call it X bar test, correct? Which is 21. This one, we call it X bar critical, the threshold, right? Which is 23. The third method, which is easy, is what? Is finding, we know from chapter 6, every value every value has a standardized value. So what we do, we standardize the whole guy. We standardize the normal distribution to be standard normal, from normal to standard. So we standardize this value. We find the z value for this. So it's going to be the z test. And this one, we standardize this value to find the z critical. That's it. We just compare them. If z test is greater than, then we reject. If z test less than, we. So again, here, to summarize, number one, if x bar tests, because this is right tail, remember, if you have left tail, it's going to be the opposite way around. If x test is greater than x critical, then we reject H node. If x bar tests less than x bar critical, we fail to reject H node. This is for what? This is for the right tail. Okay, the same is applicable with the z. Okay, this is for number one. Number two, we did already this one. We did that one. For number three, so you can copy this, put it here as number two. We can copy this, put it here. Number three is the same as number one, but with a z value. So let me put underneath them, like the z test greater than z critical. Z test less than z critical. Okay. So this is the summary of what we are doing. So next video, I'm going to show what are the math or the formulas then used, do some examples.